Did the countdown happen? Okay, I missed it. All right, so welcome to lecture 32. We're going to continue learning how to do inspection analysis of these transistor circuits. This is the circuit we'll continue to work with now, the one we've been working with for the past lecture or so. Just a few announcements. One of them, homework 10, is going to be online soon. I don't know if it's been online, taken off, but we're seeing some issues with it, and so we're fixing them. I'm sure you don't care because your lab is due tomorrow. And so, I mean, some of you are done with the lab, so those people don't care, but those still doing that, I'm sure the next homework is very far from their minds because the next homework is not due till 2 weeks from now. So your midterm is coming up, so I already talked about that. That's Friday this week. This is still the stuff from last week there. All right, so it doesn't want to bring up my keyboard, but it'll be Friday, this coming Friday, November 9th, 5 p.m. You had an information sheet about the midterm, and it contains all sorts of extra office hours and a review session. Here it is. And so you're going to have plenty of support for that midterm. I guess with that, any issues you want to talk about? There were some things on Piazza about what goes into the lab report. I answered that one, I hope. Any other issues about that? Everyone happy and comfortable? Yes.
I was just wondering for the hand design portion of the lab report.
Yeah.
Do we just give a equation for the gain of the network and then say these are the resistor values we chose and they satisfy it?
Yeah, so I think what you should do is just use those equations and plug in numbers. I mean, to me, that's where you're plugging in numbers. You're showing what numbers you plugged in because the spice plots aren't going to show your numbers, right? How you're calculating this, how you're using your equations to get certain values. And then somewhere in your discussion, you should talk about how your values match spice or not and why, and how your values in spice match measurement or not and why. And so those are the main things we want out of this, that you understand, what the differences were, what you had to do to design. So hopefully you had trade-offs you had to get around in your design. So you chose one value, then you found your gain is too high, your frequency is too low, and then you traded something off, and why is it that trade-off worked? Okay, the answer to that should have something to do with the DC biases around VCB, right? Those things that we talked about in lecture. Okay, so and the lab report is also supposed to be something where you can showcase whether you can communicate well or not. So unfortunately for some, your writing skills come into this, and fortunately for others, right? But hopefully after this, you'll all understand better, how to write up a report, because you're going to get another one coming for lab number 6 when that comes out. Okay? And so the reporting is very important, because I think for every lab that you do, anything you do, right, you think you're in the technical world right now, but you're not. Because once you go out to work, the technical part's going to be half of it. It's what you communicate that's the other half. And sometimes that's the most important half. Right? I can boast all I want about my research and this and that, but when it really comes down to it, I could take mediocre research and make it look fantastic. Every single faculty person at Berkeley can do this. And that's the difference between good faculty and bad. The work across the universities, across the nation, I don't know that you can really argue that one of them is better than the other. I mean, maybe you can argue that. The difference is one of those groups can actually disseminate the real information about that and make everyone understand how important that is. Right? So that's why we're putting some emphasis on the lab here. It's not just your technical skills in the end, it's how well you communicate what you understand and have someone else understand at the same time. Okay? So that's why in the lab, I've given you a skeleton of the lab, but it's really up to you to fill that in. And that's where you're going to have individual differences, I think, in that. And so this is your Maybe this is your dry run for this one, but you're going to then have lab number 6 where you can hone your skills even more. Because lab number 6 is going to be the same thing. Similar type of lab report for that. It's going to be a bigger design, but lab report and that sort. Okay? Any other questions about that? It is a big day tomorrow, so if you have questions, I can answer some of them.
Sorry, why is tomorrow a big day?
Because your lab is due. I could have said because it's the election day, and you can be voting, right? How many are voting here? Oh,
What?
come on.
Oh my God!
For the record, who didn't hear that, there was an "Oh my God" coming out. Is that because there were too few people voting, or?
Yeah, wait, I thought like more people would be voting, but they're not. So I'm surprised. I guess surveys about people in the technical fields really do hold true.
Ooh, he's being insulting now, folks. Go out and vote, people. Come on. I mean, some can't vote because they may not be citizens of the country. But those who can vote, go out and vote, okay? It's the best thing you can do. All right, so with that, I think I'm going to move on to the lecture. Any other questions, issues? Okay. All right, so again, today we're going to look at high-frequency analysis. And if we have time, we'll hit MOS inspection analysis. But I expect you to already know MOS inspection analysis. Because what did I say about MOS? Someone tell me. If you want to do inspection analysis with MOS, what do? I already gave you inspection formulas for bipolar. What do you do for MOS? Okay, RPi is infinity. That's great, but why does RPi infinity? Why is it? Yeah, because RPi is equal to beta over GM. It's beta that goes to infinity. Okay? So when you do your MOS, do that. And then sometime during this lecture or next, I'll tell you that doesn't always work. But for now, do that. Okay? And so MOS should be a lot easier for small signal than bipolar. It should be a lot easier. Because you don't have to worry about a lot of resistive loading. If resistances are infinity, there's no loading from the next stage. Right? The gains are 1 for some stage-to-stage gains. Okay, so let's get to this amplifier again. So we went through this whole thing. We got the input, we got the DC bias point, we got the input and output resistances, which I did by pure inspection. Okay, and that's only because I have those resistor load resistance equations in my head. Then we got the gain from stage to stage. Okay, and we finally got the gain expression. And so I'm not going to go through all that again, but I sort of summarized all that we did in sort of a step-by-step procedure for mid-band gain inspection. So that step-by-step is 1, identify and label all signal path nodes. Maybe I should have a picture up when I'm going through that. So here's that picture there. So 1, 2, 3, 4, all the nodes. And we're going to get the gain from each stage. So get stage gain from node to node. And so for each stage, be sure to account for loading by the next stage. That's why you need those resistance equations in that inspection analysis sheet. Okay? And you're going to need them again and again and again. So even if you don't like to memorize things, you will if you've done enough problems. And so how you do on this midterm may just be information for me and how many problems you've done in the end. And again, the more problems you do, the more perfect you get at this sort of thing. For transistor terminal to terminal gains, you'll need to likely need to determine an output node resistance. Okay, to ground. Okay, that includes the loading by the next stage, and it even includes the loading by the previous stage if you're, say, determining something like the resistance going into the collector of a transistor, or even going up into the emitter of a transistor. And remember, those formulas go all the way back to what's on the base terminal. And so then take the product of all node-to-node gains to get the total gain. Okay? And now you can do all of this by inspection if, 1, there's no feedback. If there's feedback in your circuit, then you need to be careful. Some of them you can inspect. Some of them it's just safest to go back to hybrid pi until you go to 140 and you learn some better feedback techniques. But if you see feedback in your circuit, be careful with your inspection analysis. Okay? And if you don't know when to be careful, just don't do it. Yes?
You can use the Miller effect for resistors too.
Yeah, you can. That's, well...
Because it looked like the Y...
No, I would say don't do it. Don't do it for even, for the Miller effect. It's better to go to hybrid pi. Just go to hybrid pi. For things simple enough we're talking about with the resistor and feedback, just go hybrid pi with that. Okay? So there's no feedback. You know all the terminal-to-terminal gain equations, or you can see or derive them quickly. Okay? You know all the equations for the resistances looking into the transistor terminals to ground, or can see or derive them quickly. By see or derive, I'm talking about I'm looking into this transistor. I know I've got R pi there, but I know that I have a different current running through RE as the base current, so RE has got to be something different than RE. Okay? And so that, to me, is following the currents going through this. And finally, you can see or derive quickly. So I just said that, by following the currents there. Okay, so that's inspection analysis in a nutshell. In case you didn't quite get the gist of everything that I was doing last time, read through this, look at what I was doing last time, get the flow of how to do inspection analysis. Hopefully you've already done a little bit of that too. But the next thing I want to talk about now is frequency analysis by inspection. Okay? And so it's a similar sort of thing. You identify and label all the signal path nodes. You draw in the small transistor capacitors. So that's C mu, C pi, or CGS, CGD, those types of capacitors. Use the Miller transform to transform any feedback capacitors. Well, not any feedback capacitor, just the feedback capacitor from base to collector or gate to drain into two shunt capacitors. Okay? And then for base to emitter or gate to source capacitance, we can't really handle that. That's like a feedback capacitor where the Miller effect doesn't quite work correctly because of the type of gain it is. It's positive gain across. The gain about 1 is what it is. So you need to know the equation for the driving point resistance for that one. And then get the time constant for each node. So determine total node capacitance, node resistance, that's a time constant, R node times C node. Then you handle the feedback capacitor separately. You add together all the time constants. So that's in a nutshell how you do it. Now I'm going to do it for you. Okay? I don't mean to just show that. I'm actually going to do it for you for that circuit that we were looking at. So let's go back and to the original circuit here. And actually I could just use this circuit right there. So to do my high frequency analysis, I need to draw my small signal circuit again. So I guess I'll do that here. Let's go ahead and draw this whole circuit again here. And the difference this time is I'm going to put in all the little capacitors that I'm going to have to deal with in this circuit. So right now I'm just redrawing this. So I got RS, RBB, that, and I'm leaving a lot of space here because I'm going to put a lot of capacitors in there. That's going to Q1. The small signal circuit had this RE1 that stayed back, or that stayed there because of the way that I chose my bypass capacitors. And then I have a collector resistor here, RC1. I then feed this into my next stage, which is Q2. It also has an emitter resistor, RE2, and this then goes out into RL to my output voltage there. Okay, so that's my basic small signal circuit, the same one that we were playing with last time. And so what's the first thing on my list that I want to do is I want to draw in the capacitors that matter. Okay, I've already shorted out all the big capacitors, the bypass and coupling capacitors. You know to do that. I've shorted out or zeroed out all the independent sources, so all my voltages, or sorry, all my independent DC sources. So these VCCs went to ground up there. And so now I'm going to draw in my capacitors that I care about. So one of those capacitors is going to be C pi of device 1. Another capacitor is going to be C mu of device 1. And another capacitor for device 1 that I'm going to include is the CCS of device 1. Okay? Just for the heck of doing it. Sometimes it's important, sometimes it's not. I think your book ignores it quite a bit, but I'm leaving it in there so when you go to 140, if you can go to 140 next semester, you're going to use CCS every now and then. And so those are my capacitors for the first transistor. For the second transistor, it's the same thing. I'm going to have a C pi 2. I'm going to have a C mu 2. And I'm going to have a CCS2. Okay? Those are the capacitors I have to worry about. And in this problem, yes, I did have a load capacitor that I put in CL, which I assume would be a small capacitor. I think I said it was 50 picofarads or something when we began with this. So because it's only 50 picofarads, we have to worry about it. Okay, just like in your lab, you had to worry about that 68 picofarad or whatever we put at the output of your lab. Okay, so I'm going to have to worry about that capacitor too. Well, the first thing you do after you put your capacitors in is you figure out which ones matter and which ones don't. Okay, that's going to be a big thing because that's going to allow you to save a good amount of time. So these capacitors, C mu 1 and C pi 1, they're going to matter. Well, there's some debate after we're done with this whether C pi 1 matters. Wow, that was loud. That's why it was loud. It's at 100. And so I can look at these capacitors. I see they all belong except, look at CCS2. CCS2, this node is going to ground there. And that means CCS2 is shorted. Right? See that? And so because CCS2 is shorted, why am I even going to bother with it? I'm not. Right? It's shorted to ground. Okay, so I'm getting rid of that capacitor. And in most circuits like this, when I have many more transistors, I'll be able to eliminate even more capacitors than that. But you want to eliminate your capacitors because the more capacitors you have, the more work you have to do. Okay? And so the next step that I want to do, I guess I skipped one of my steps, and I guess my first step in this thing was to label the nodes. So let me label these nodes again. And so I'll do it like I did last time. There's node 1, that's node 2, that's node 3, and this finally is node 4. Okay, and the reason why I'm labeling the nodes, I'm going to get shunt capacitance at the nodes, and that's going to make my job a lot easier. Yes, question?
So if we neglect CCS2 because it goes to ground, why do we keep CCS1?
I'm sorry, it's going to ground here, but it's in parallel with a short to ground.
Oh,
yeah, it's been shorted out, is what it is. Okay, so the next step that I want to do, and I can either do this or I can memorize the equation for C mu 1. So I have the equation for C mu 1 memorized. How many of you have it memorized? C mu 1. Okay, I see this sort of thing and that sort. Yeah, okay, a lot of these sorts. I don't see any strong, yes, I have it memorized. I see this kind of thing going on, okay? And so if you're that type that has that kind of thing going on, I highly recommend that you remember the Miller effect more than you try to memorize that equation. Okay? Now let me first title this before I... Okay, so for that Miller thing, I'm definitely going to borrow stuff here because I don't want to redraw this whole thing. So if you're taking notes, you're going to love this. Some people take notes because it helps them to remember and understand better, and I'm a believer in that actually. If you take notes, then I agree that it'll help you remember things, but it is true because you're getting the notes, you don't need to take notes.
Professor, I hear some of my peers saying that they have, because they're taking notes on electronic devices, they also can simply copy and paste.
Oh, I see.
Joke's on you.
Oh, got it. Got it. Yeah, okay. That's great. I like that. So I could stop making my joke that you're not going to like this when I do this. Huh? All right, so here's what we're going to do. We're going to take our C mu capacitance, and we're going to not think about it in that position. Okay, I'm going to take C mu, and I'm going to stick a Miller capacitor right here. And what's that Miller capacitor going to be? C mu 1 times 1 minus the gain, but the gain is,
transfer.
you're right, let me just do it that way. Well, okay, I guess I'll do it this way. GM1 times R at 3, right? That's the gain. Let me write it out your way first, just so it's very clear. So minus the gain of stage 1, which I'll call AV1, right, which is going to be equal to C mu 1 times 1 plus in the end, because the gain AV1 is minus GM1 times the total resistance at node 3, right? That is my Miller capacitor there. And so because I did that, I no longer have to worry about a capacitor and feedback. I don't need to know that equation. The equations will fall out just from what I'm doing right now. Okay? The other part of the Miller capacitor shows up here. Remember, the Miller capacitor is both at the input and the output, and this is just going to be equal to C mu 1. Okay? Everyone get that? Yes?
But why the signal don't go to the, I mean, how can you directly go to the ground? Because in the hybrid pi model, the signal is like from B to E, right? But you have the resistor RE there.
In the hybrid pi, C mu 1 is from B to C.
Oh, yeah. B to C, and when you use the
Yeah?
you have to divide it from B to E.
No. Miller theorem is from B to C, or it's from anything that has gain. And so you got a lot of gain from B to C. From B to E, you don't have much gain. B to E is going to be gain less than 1 if you've memorized your equations, which is why the memorization is extremely important. And so so this C mu 1, right, this is exactly where the Miller effect, I'm not going to say what it's made for, but this is where it's most applicable. You got gain from B to C, and so I'm taking something in feedback, and I'm breaking that feedback and just having shunt values in those nodes. So you should review the Miller stuff there, and you'll see that what I'm doing is exactly what we went through that other lecture. Okay? Okay? So that's how I'm handling that C mu there. How about the C mu 2? What am I going to do with that?
Collector to ground.
C mu 2. Yeah, I heard it.
Goes to ground.
It's already shorted to ground, yeah. I don't have to use any Miller effect on that. See, its other side is going to ground. And so that's just shorted to ground. It's shunt to ground right there. Okay?
Why is it shorted to ground?
Because this is a short up here. Can you see where I'm pointing? This right here is a short. See, the other side of C mu 2 goes to that short.
Oh.
Okay? So it's not, there's no gain across that. I don't have to do any Miller or anything like that. It's just a capacitor shorted to ground. That makes it very easy to handle. Okay, how about C pi 1? What am I going to do about C pi 1? I can't do anything. C pi 1, I'm going to have to determine what the driving point resistance is. Yes?
Does the Miller effect not work from phase to emitter because there's no gain, it's just minus 1
So the reality is it does kind of work. And so I want to save this to the end, but let me save that to the end. Because if I don't save it to the end, you're going to think, what did you just do that for? That's useless. Okay? So I'm going to derive what that capacitance is. But right now with these, or what that driving point resistance is, but right now with all these capacitors, I can write something out for my open circuit time constant analysis here. And so using open circuit time constant analysis, let me go back, it's the right color, I'll go here. I'm going to write out my omega h now, and I can write out its equation without really putting in the values yet. But with 1, there's nothing there, right? There's no capacitance at 1. I don't care about node 1. Okay, but node 2, I've got capacitance to ground, I've got resistance to ground. Okay, so I want to take all of my capacitance to ground here, which I'll call C2 circle, and all of my resistance to ground from node 2. And so when I use that nomenclature there, I'm basically saying that this is the total shunt capacitance at node 2. Okay? And this is the total shunt resistance at node 2. Okay? I haven't determined what those are yet. I'm just telling you what those are. That is a time constant associated with node 2. Okay? Then I'm going to go to all nodes. I'm going to do the same thing. I'm going to find the total shunt capacitance at node 3, the total shunt resistance at node 3. I'm going to multiply them together because they're going to make a time constant. I'm going to take the total shunt capacitance at node 4, the total shunt resistance at node 4, multiply them together to make a time constant. And then I'm going to take those capacitors that I don't know what to do with yet, C pi 1, and multiply it by its R pi 1, which is its driving point resistance associated with that capacitor. I don't know what that is yet because I have to derive that. And then I'm going to have another one, C pi 2, times an R pi 2. Okay, and that's 1 over all of that. And that then is going to be my total omega H. Right? All I'm doing is getting the time constants associated with every capacitor that I've got in here and adding them together and then taking the reciprocal of that. Okay? And that's how you do your high-frequency analysis, but let me first tackle these things, right? We haven't seen these yet. So we need to determine the driving point resistances, which I'll just call R pi knots. Okay? So let's go ahead and do that. So let me go to the next slide here. And let's do it for a general case. And so the general case is I have my generally loaded transistor here. That you've seen before. I have this C pi, and I'm trying to determine the driving point resistance associated with that C pi. And so how do I go about doing this? I plug in that hybrid pi model. So there's ground. There's that RB resistance again. That you know is going to go into the R pi of my transistor. I'm going to call the voltage across that R pi as usual VBE. In place of C pi, I'm going to put a test voltage source from which I want to see the test current that responds, or how the circuit responds to that test voltage source. Then I'm going to have a GM times VBE here. I'm going to have an R naught, and then I'm going to have an RC going to ground. And finally here, I have my RE going to ground. Okay? So that's the circuit now that I have to analyze in order to determine what that driving point resistance is. And so this is a analysis that hopefully you're very comfortable doing now because we've done it many, many times. I don't know how many times you did it for your homework. Hopefully a few times, unless you inspect analyze the whole thing, which would be fine too. But I doubt you did because I think the homework was due a little too early for you to do a lot of inspection analysis on that. But if that's the case, that's good because you need to get that practice with the hybrid pi. But what I would do in preparation for the exam, go back to that homework, redo those problems with inspection analysis. Okay? All right, so let's tackle this now. Let's do Kirchhoff's current law first right up at this point right here. Let's do a KCL right there. And if I do that, then I can say that my IX current is just going to be equal to the current going through R pi, which is just the VBE over R pi, but VBE equals Vx, right? So I could say that Vx equals VBE in this case, right? You could see that right from this circuit right there. So I'm going to write that as Vx over R pi. Okay, plus it's going to be the total resistance across RB. If I define this as a VE across RE, then the total voltage across RB is VE plus VX over that RB. Okay, and I can expand this out because I'm going to handle these voltages individually. So this is going to be VE over RB plus VX over RB. So I can see two VX's in there already. And so now I don't like that VE. I want this only in terms of IX and VX, of course, so I have to replace VE. And so I now want to know what VE is. And from this circuit right here, I can say that all the current going into RE times RE is equal to VE. So VE is just going to be equal to RE, capital E, times all the current going through that. And the current going through that is this current going through R pi, which I already said is Vx over R pi, plus the current, let's do the next current. So Ix is going out of that node, so that'll be minus Ix, and then plus this current coming from there, Gm times VBE, but VBE is just Vx. Okay, and I'm going to ignore R naught as I usually do. And just say that it's large. Okay, and so those are all the currents going to that. That creates VE, and so combining these two together allows me to write an expression for Ix finally. And that's going to be Vx over R pi plus Vx over RB plus this quantity here divided by RB. So this times all that stuff. Vx over R pi minus Ix plus Gm times Vx. Okay? And then finally, and I'm doing all of this sort of for you so that you can see how you should attack these problems that have a lot of math. Not a lot of math, but a lot of algebra. Right? Put all the Ix's to one side. RE over RB. And then I guess I'm forced to write this whole thing. 1 over R pi, 1 over RB, plus RE over R pi, RB, plus GMRE over RB. Okay, and you could keep doing a lot of this math, but the form that you usually want these to be in, so now I'm now going to skip a few steps, but I'm going to say that this R pi 0 is going to be the Vx over Ix. But in general, what I try to do is get it in a form where I have 1 at the top. I got the reciprocal of something. So I've got 1 divided by a whole bunch of stuff. And in the end, the whole bunch of stuff that you're going to end up with is an RE plus RB divided by R pi times that RE plus RB plus 1 plus GM RE divided by RB plus RE. And so these two, of course, will cancel out. Now I've got 1 over R pi and 1 over this thing here. And so anytime you see that 1 over thing, you can always write this in a very compact form. And so in this case, that's just going to be R pi in parallel with the reciprocal of this, which is just RB plus RE over 1 plus GMRE. And this now is equal to my driving point resistance, R pi naught. Okay? And so anytime you do something like this, you always want to look at the equation and see what happens with it. So if I go to the other side here, let's do that, and let me rewrite R pi naught is equal to R pi parallel with all this stuff, RB plus RE over 1 plus GMRE okay. And so I could take a few cases here. So if I have RE large, I'll write that here. if I have a large RE in this thing, then this ends up going to R pi in parallel with 1 over GM. Okay, and 1 over GM is how big? It's small. So this is going to be a very small resistance. And the reason why I'm showing you this is because oftentimes it can be neglected. In other words, the time constant I get from this resistance is oftentimes going to be very small compared to other time constants. Okay? And so another way to understand that is if I have something like this, where that C pi is, if you had to tell me what the gain was across this, VI to V out, what is that gain? No, 0.7 is the DC voltage drop across it. What's the gain? Small signal gain. Signal here to signal there. Basically a voltage divider, you see. Right? It's kind of like that. How big is RE? Maybe that's 1 kilo ohm. How big is 1 over GM? 25 ohms. Gain's about 1 across this, right? If the gain is about 1 across this, then if I have some voltage V1 here, I'm also going to have that same voltage V1 there, right? Which means how much voltage have I dropped across my capacitor? Nothing, right? So the voltage across this capacitor, that voltage here is V1 minus V1, that's 0. If I have 0 volts across my capacitor, what do I say about it? It's not there. So, if you're in a crunch and you're trying to determine the omega H, okay, and you're in a crunch and you just don't have time to write the thing down, or if you're just lazy and you don't care about the 1 point or maybe 0 points you'll lose for not including it, just ignore it, right? Just take into account all the other time constants that'll be much larger than the one contributed by C pi, right, because C pi's got virtually no voltage across it. Ignore it. And so that's one way you can do these problems here. If you see this, you can either memorize that equation. I have it memorized in case I have. Now you can't do this if there aren't other dominant time constants in other places. If you have no other dominant time constant, you better know this equation here. But if you know that there's some Miller effect going on and some big resistance across that Miller effect, neglect this capacitor. Yes?
Wouldn't C pi by definition have 0.7 volts across it?
But that's a DC voltage, right? So we're worried only about AC voltages. Capacitors are only there for AC voltages. For DC, the capacitor is an open circuit, right? And so it's only the AC sense. And in the AC sense, I have the same voltages on both sides. Now, I could have some phase difference between those, in which case, I might not be able to make this complete argument all the way at super high frequencies. But this is, if you're in a time crunch, don't put it down. If you're not in a time crunch, put it down, right? Especially on an exam. Only on an exam, I would say. Right? When you're doing a real analysis, I generally neglect a lot of the C pi's. Yes?
Where's that 1 over GM coming from?
That's little re. So that comes from the derivation. And so the other way you can look at it, if you want to follow the currents, that thing is to look at it from the T model. Yeah, there'll be an R pi there, but the R pi is in a different place. So when you do that analysis, you'll see that this becomes 1 over GM as well. Okay, but you have to go back to those analyses. But it's very easy to see right here from the T model. right away you can write that V naught over VI is that RE over 1 over GM plus RE. Okay, right away. But I hope you don't have to think of the T model. If you do, that's okay. Right? But hopefully you can just look at this, see the transistor, not see the model, and just looking at the transistor, you know what that is. Just like you look at a resistor, you know V is equal to I times R. Right? That's the comfort I want you to get to with the transistor. It's more complicated. It's got 3 terminals. You've got different gains across it, different resistors, but there's not really that many equations to memorize, I think. All right, so maybe my 6 is a little less than it really is, but you know, it's a little amoebic there, right? Because there's Miller effect and all. So I'm sticking with my 6 equations. Okay, that's really all you really need to know. All right, so let's continue with this. So I've derived that now, and so now I can go ahead and write the total expression for omega h. So now, get the taus to get omega h. So let's start with, we go back to my omega h equation here. There it is. Let's start with the capacitance at node 2. Let me get to this here. Okay, so the capacitance at node 2, what is that capacitance? You tell me. I got this C mu 1, right? So that Miller capacitor, C mu 1 times 1 plus that big GM of 1 times the total resistance at 3. What is that big GM 1 times total resistance at 3? That becomes C mu 1 times 1 plus, what's big GM? You should have this in your head here. It's this equation. Yeah, you said that, right? GM over 1 plus GM RE. All right. Oops. So I'm just going to write that down. So that's going to be GM1 all over 1 plus GM1 times RE. And then I'm going to multiply by all that resistance I see at node 3. And so all that resistance I see at node 3, I should have done it this way, so I'm going to do it this way. Let me rewrite that down here. I just need the space. That should be RE1. Okay, and so that's going to be multiplied by, I first have RC1 looking up, right? That's the resistance I see looking up into ground. That's going to be in parallel with all the resistance I see looking down into the collector of Q1. What's that? That's R naught of Q1 times 1 plus GM of 1 times that RE1 divided by 1 plus all that resistance I see looking out of the base, which is RS parallel with RB divided by R pi. That. Okay? That's a lot to remember, I know. But watch what I do at the very end of this. And then I got one more resistor because I got to look out forwards too. I got to take into account the loading from the next stage. So the loading from the next stage looking into the base, what's that? Yeah. R pi 2. Yep. All right. Someone has memorized their equations. Yep. Times the RE of 2. But the RE of 2 I can combine actually with, I have to get that total RE out there, looking out of that. So that's going to be RE of 2 parallel with RL. Okay. I can even also parallel it with R naught of 2. Can you see what I'm doing there? Let me put a little divider here. Okay? That's the resistance times all that there. Hopefully you can tell what I'm doing. But even if you can't, it's not going to matter because what am I going to do to this whole thing? That's right. Someone said get rid of it. That should be your goal in all of these things. Just get rid of things. That's large. This is large. Because those things are large, I don't care about those things. And so the end result of this is going to be C mu 1 times 1 plus GM1 times that RC1 divided by 1 plus GM1 times RE1. And that's the capacitor due to that node. Okay, I spent a lot of time writing out those big resistors. On an exam, if we ask you for the explicit equation, you should write out those big resistors, but if we don't, just write down RC1. How's that resistor there? Okay? Everyone see what I did? All right, and so with C, that's not enough for this. With C2, I need to have an R2. I want to keep the circuit up on that side there, so I just moved on. What's the R2 there? So first of all, do I have any other capacitance I have to worry about at node 2? How about C pi 1? No, I'm not going to worry about that because that's a feedback capacitor. I already determined its driving point resistance separately. Okay, I already covered that capacitor. And so for R2, what's the total resistance in shunt? Well, I see RS going that direction, to the left. I see RBB going to ground as well. I see, what do I see? R pi of 1 plus beta plus 1 times RE of 1. Excellent. Good. You're getting the hang of it there. And so with this, because this thing is large, probably compared to all these other things, right? RS usually isn't that big. I could just say that this is equal to RS parallel with RBB, and I probably will even be able to do that, right? Depending on the size of it, because right, if I've designed this correctly, R1 and R2 should be big resistors compared to RS, just like your lab. Right? And see how everything just falls apart and simplifies to something much easier for me, which means after all this stuff, I could say that my tau at node 2 is just C mu 1 times 1 plus that GM1 all over 1 plus GM1 times RE1 times RC1, and that whole thing times RS. So that's tau 2. Now I got to do that for all the rest of the taus. Okay, so now I got to go to node 3 after that. And so for node 3, I'm going to get a C3, and now I'm going to go a little faster with all these things. At C3, what do I see? I see that CCS1. Okay, what else do I see there? I see a C mu 1 hanging off there. And then I see C mu 2 going up. Okay, now the resistance at node 3. All the shunt resistance with node 3, what do I have there? Well, I've got RC1, and I'm again going to be complete about this. We have everything that we just wrote down before. And why I'm writing all this down again, I think just to be complete, since you're learning all of this stuff. But this is the stuff that we just wrote, and I'm just writing it all again so you get very clearly that whole thing, but you know that all this stuff is large. So this whole thing just goes down to RC1. And so I can write down tau 3 as just CCS1 plus C mu 1 plus C mu 2 times RC1. Okay? Very quickly, I've written down that time constant there, only because I have all of these things in my head. And now I can keep pressing forward with the rest of these. Let's go green now for C4. So C4 is what? What's the total capacitance in shunt with 4? And so all I've got in shunt with 4 is that CL capacitance here, right? Which I started off with in the original circuit. That's not a transistor capacitance. That's just the load that I said we had. And then I need to get the total resistance at 4, at node 4. And so what is that resistance? Well, I see RE2 going to ground right there. I see RL going to ground as well. I have R02 heading in that direction, right? Also going to ground at the top. Of course, why am I writing down R02? I usually say it's big. I'm going to do it again, but I'm just being very complete about this now. And then finally, I've got another resistance here that is this resistance across looking up into the emitter. And if you remember, that resistance looking up to the emitter is R pi of 2 all over beta 2 plus 1, but plus everything I see looking out of the base, which you know is a pretty big resistor, RC1, well, it's big in form, times R01 times 1 plus GM1 times RE1 over 1 plus RB parallel RS over R pi 1, that resistor there. Okay, and all that is over beta plus 1, but you know that this whole thing just reduces down to RE2 parallel RL, and then parallel this R pi 2 plus RC1, right, because this is large, divided by beta 2 plus 1. Okay, and then finally, I'm out of time. Finally, my fourth time constant here is going to then be equal to this CL capacitance times all that resistance that I just wrote down. RE2 parallel RL, and then R pi 2 plus RC1 divided by beta 2 plus 1. Okay? And so now I have all the node time constants. I still have those C pi time constants, but we just derived what those equations were for C pi. So first thing next time, I'll just write down the whole solution for omega H. But you see how we went through that, and we went through that very quickly by inspection, by just knowing how to look into the nodes and seeing all the shunt capacitance. Okay, see you next time.